How do children count? You may have observed this or even done this yourself. The way children count a certain set of objects is they point at the first object and say 1 out loud, and then they point at the next object and then they say 2. And they keep going until they run out of objects. And once they're done, they know the amount of objects, which is the last number that they exclaimed by pointing at it, right? So even children know intuitively to make this correspondence, this association between a set of objects and a set of numbers to count it. And this is exactly what we've been doing when we defined bijection. What does it mean for two sets to have the same amount, right? Now, last time we defined what it means for a set to be finite, which simply means that it can be put into correspondence with some natural number. And I gave a rather proof that ended up being a little too technical for my taste. That is okay. We will try to do more intuitive stuff today. But to continue with this spirit of finiteness, there are a few things that I want to mention. So, according to our definition, if I want to convince you that something is finite, I need to tell you how many elements it has, right? Because our definition says it has to be put into bijection with some number. But, well, what is that number? To find that number, we have to count the objects. That is not very practical, because if I tell you I have a set, and for some reason, with the theory that I have, I know that this set has at most 1 million elements. Well, you can be sure that this set is finite, even if I don't tell you exactly how many elements it has. Maybe it has 10, right? So we have to weaken our definition a little bit for it to be useful, because sometimes we don't want to specify what the amount is. Let me just write something down. I don't know if I've given this definition before. I suspect I have not. So for two sets, AB, we write A is less than B. The cardinal of A is less than the cardinal of B. We didn't define cardinal number, but we don't need to, right? We can just use the symbols whenever there is not a bijection, but an injection, right? So there is something that associates uniquely every element of A with a unique element of B. No repetitions, but maybe B has elements that aren't matched, right? This function, let's call it f, doesn't have to be surjective. And I don't care, because this is defining when does A have at most as many elements as B. In the example above, if the child continues to count but gets tired after the number 5, the child can be sure that there are at least 5 objects, even if it didn't, if they didn't finish counting, if that makes sense. Let me define a few properties of this symbol, so proposition. And these properties are either, interestingly, they are either very easy to prove or very difficult to prove. And this is interesting, this phenomenon, right? That there's sometimes it's hard to find a middle ground. So the first property that I want to draw your attention to is that if A is less than B and B is less than C, you know this property, right? You've seen this with many examples, like the subset relation or the divisibility relation. This is called transitivity. So this is not really an order relation for the same reason that the last one wasn't an equivalence relation. The bijective wasn't an equivalence relation, but it behaves as an order, right? It's a sort of ordering of the cardinals, right? The second property that I want to talk to you about is if A is less than B and B is less than A, then, well, of course, you would expect these two sets to have the same size, right? This is how these two ideas are connected. The converse is obviously true. If there is a bijection between A and B, well, this bijection and its inverse are both injective, right? So the converse is trivial. The converse is, maybe I should write it as a converse. with the converse, I mean. So this is an if and only if. The backward direction is very easy. The forward direction is actually probably one of the most difficult theorems that I have mentioned in the course so far. And we can talk about it next time if you want. On Thursday would be our last class to talk about this. But it is surprisingly challenging. I will add the reference in a second. This is called anti-symmetry, if you recall from what I defined in the very first chapter. Anti-symmetry. And let me see the chat. Oh yes, you can use this as given on the problem set. We will prove this. The easy ones we will prove right now, or at least I'm going to tell you how to prove them, even if I don't write it down explicitly. But yes, this is so elementary that you should be able to use this. Otherwise, what's the point of having covered this? So yeah, that's a really good question. Let me see. What else? Okay, here's another easy one. If A is a subset of B, then of course A cannot have more elements than B, right? I don't know if there's a name for this. Yeah, maybe I shouldn't even make one up. Property 4. Oh, there's one that I could have written before. Any set has at most as many elements as itself. This is reflexivity, reflexive, right? This one is also pretty obvious. There's another one for any A, B sets. Either A is less than B or B is less than A. And this is called linearity. You recall you don't have to remember these words for the final exam. I'm just writing these down because they connect to ideas that we've talked about in the past. And many other courses do use these words, right? There's a lot of relations in math that are transitive. A lot of them are anti-symmetric and so on. Let's try to maybe give a proof sketch of the proof. The reason this is a sketch is because I don't want to spend too much time doing things that you already know how to do. So can anyone tell me in one sentence how you would prove number 1? Then I will tell you how not to prove number 2. But I will give you the reference. So this is the Cantor. Some people credit Schroeder with this as well, but other people don't. So I'm not really sure. I haven't looked into the history of this theorem. But the way I understand it is Cantor defined all of these notions about cardinals, and he did come up with this theorem, but his proof was wrong because, like I said, this is surprisingly difficult. And then Bernstein corrected it. That is the version of the history I have, but don't quote me on this. So this is the theorem, and I'm just going to add a note that this is actually very difficult. We could totally cover this in one lecture, and you would understand it. It's not difficult in that sense. It's difficult in the sense that it is surprising for something this elementary. You would not expect this to be this challenging, right? But if you want, you can spend some time trying to prove this yourself, and you will realize that you will get stuck in certain things. Let me see. Sorry. Okay, some people have answered in the chat, including directly. Okay, thank you. I think all the replies I see, including the ones that are private, are correct. So indeed, if you want to answer this in one sentence, is that the composition of injective functions is injective. And this is how you prove this, right? There's an injection from A to B. There's another one from B to C. So the composition is an injective function from A to C, and we're done. So good, very good. What about number 3? Number 3 is also easy, right? You would expect this to be almost immediate. A subset cannot have more elements than the set is consisting of, because a subset is the set having removed something from it, right? So if we want to conclude that A is less than or equal to B, what injection can you suggest? And while you think about that, I can tell you that number 4 is trivial, right? The identity Actually, you can prove something stronger. So A, B implies A, B, right? If they're equal, well, then they're less than or equal to each other. This is slightly stronger statement because every set is in bijection with itself, right? The identity is a bijection. Okay, the inclusion function was suggested in the chat. Correct. So the inclusion is bijective. Sorry, not bijective. I was thinking of the identity because I was talking about the other one, ejective. Sorry about that. So the inclusion, sometimes denoted with an I, sends every element, so I, they, to itself. This is obviously injective, right? For the same reason, this other function that I mentioned, the identity, is also injective. It's actually bijective in this case, but doesn't really matter. Now the number 5, I won't prove because this one is actually surprisingly difficult as well. And even though I should say that you can use this, you will never really use this. You will never need this. And that's a bit weird to explain why this isn't as useful as you might think. Okay, so any questions? These are very elementary properties of the less than or equal to. And I already told you how it's connected to the equal sign, right? It's basically an order, and the other one is treated as an equality. As an equality, I mean. Okay, so let me give you one more definition that we can play around with, and then we will do a lot of examples so you know how you prove things in this context. The definition, a set, let's call this X, because why not, is countable if the size of X is at most the size of the natural numbers. You know what this symbol means. It means there's an injection from X to the naturals, right? And before I do this, maybe I want to add one more thing. Yeah, let's add this to the elementary property so that you can use it, because this one is actually very useful. Number 6, A less than B. There is an injection from A to B if and only if there exists, sorry, let me write this. There exists a surjection from B to A. And to prove number 6, you prove this in problem set 1. It is either a combination from an exercise that you turned in and one of the additional exercises, or it is one of the ones you turned in. I forget right now. So it is either something that you had to turn in or something that combines something that maybe you didn't have to turn in. Anyway, we can talk about this in more detail if you don't remember how this is done. But there is an injection from A to B if and only if there's a surjection that goes the other way. And from a sketch, this is easy to see, even with this simple example with the children counting, right? There's a surjective function from this set of numbers, of objects, to the other set, because we managed to cover all numbers that the child managed to count, right? So there's a surjection from this set to the other. Okay. So now a set X is countable if and only if that happens. That also means there's a surjective function from the naturals to X. In other words, a set is countable if and only if it is a sequence. It is a sequence of something, right? So maybe let's start doing some examples. What countable sets do you know? So the naturals are countable, right? The following are countable. The natural numbers are countable because, well, this is property, what is it? Property 2. No, sorry, property 4, right? Any set is less than or equal to itself, right? So the naturals are obviously countable by definition. What other countable set? The empty set falls into this category, right? There's an injection from the empty set. more generally, any finite set. Can you give me another example? Let's start writing the surprising examples, perhaps. If this is the first time you're seeing this, this might be a bit surprising. The integers are countable. N cross n. Let me think about n cross n. Is that something that I want to do right now? Okay, n cross n is a really good example. So we're going to add this maybe after this one, n cross n. And the rationals. Now, let's just consider the positive rationals because it is easier to write down, but the same proof works for the rational numbers. I just want to save a little bit on notation. Okay, so let's proof this example. Proof. So the number one follows from the above proposition, right? This is almost trivial, it's obvious. Now, how do you show that any finite set is countable? If A is finite, then there is a bijection f from A to some natural number, right? For some n natural number. And here, let me just remind you in case you forgot, this is the set 0, 1, all the way to n minus 1. This is how I'm treating this as a convention, which might sound weird. It might sound weird, but it will never ever lead to a mistake because this is actually what it is in terms of set theory. If you don't like that convention, then you can just write the set 0, 1, 2, 3, all the way up to n minus 1. That's perfectly fine. Okay, so how do we continue? We know that there is a bijection between A and n, meaning A has precisely n elements. Why does this mean that A is countable? In the meantime, we can think about number 3. Whoever suggested n cross n is countable, do you know how to show that it is countable? Someone's asking in the chat if it shouldn't be injective. Yes, we want an injective function from A to the natural numbers. So how do we, but that's the conclusion that we want, right? Okay, so the next suggestion in the chat says we just expand the codomain to be n, and it would still be injective. Okay, so since now it is not only true that n is an element of the natural numbers, but thinking of this as a set, it is actually, well, a subset, right? So this is a subset. Then we have that A has size n, or if you want like this. Maybe I can add one more step just in case you don't like this notation, which is like this, right? And this has at most size the natural numbers because it is a subset. And now we just use transitivity, right? So by transitivity of the less than or equal to, right? Transitivity of injective functions. A has less than or equal to n, so it's countable, and we're done. Right? Always keep these arguments as simple as possible. If there's no need to define an injective function, well, don't. Just write it like this. Okay. Why are the integers countable? This seems counterintuitive. It would seem that there's actually, you know what? Let me add one more intermediate so that we can go very, very slowly with this. So 3, 4, 5, 6. Even numbers. Even naturals. Right, so 2n, this set. Why is this set countable? Well, in this case, it's just a subset of n. So let me think of a way of making this harder. You know what? Maybe this isn't necessary. Yeah, let's just remove this. Yeah, I mean, we can construct, sorry, do you want to keep this example? Even naturals are the same size. This is obviously countable because it's a subset, but of course we can say more, right? Same size as the naturals. So why are the even naturals the same size? This is counterintuitive. Why? 2, 3. So on the one hand, we have the natural numbers, and on the other hand, we're skipping 1 every other, right? 0, 2. Why would these be the same amount? Shouldn't there be half as many even numbers? So notice that if I take any natural number and I double it, this is a bijection, right? From n to n. So the natural numbers have the same size as 2n, right? So this is a bijection f, and it's sending 0 to 0, 1 to 2, 2 to 4, 3 to 6, right? So someone is asking in the chat, are we supposed to compare infinity? Yes. So the big surprise out of all of this is, of course, that there are infinite sets of different sizes. Not all infinite sets are made equal. Right now, we haven't proved that there are any infinite sets of different sizes, but this is not too difficult to do. Now, let's just continue with these examples, or then we can talk about something else. So, sorry, someone suggested this already in the chat, right? So we take f of 1 to the negative 1 and all natural numbers to the additive inverse. Right. So we need, what do we need? We need to define a function from the integers to the natural numbers that is injective. How do we do this? How do we cram in all integers, including the negative ones, into the natural numbers? So this has sometimes been called the problem of a Hilbert infinite hotel, right? So the idea is that there's a hotel, H, and it has rooms labeled 0, 1, 2, 3, and we need to accommodate integer many people, right? How do we entertain all these guests? Can we find a room for all of them? That is exactly the problem we're trying to solve now. How do we cram in an injective way? Like, we cannot put 2 people in the same room because, I mean, it's a hotel, right? What kind of a hotel would it be if different people are given the same room? It would be like a hostel or something else. Anyway, so how do you solve this? How do you solve this? Okay, so we can ask each person to move to double their number, right? So that would work if there are already people in the hotel. But let's say the hotel is empty. I just want to accommodate integer many people. So I think that is the right idea, right? We just have to expand it out a little bit. So where do we send the nth person? And keep in mind that n is an integer. It could be negative, right? So maybe we send the non-negative ones to a different place and the negative ones somewhere else. right? Why don't we send the non-negative ones to 2n, as someone in the chat suggested? Maybe it was private, so other people cannot see it. That's fine. Okay. So someone else also wrote something. So Ray is suggesting we alternate. We alternate the negatives and the positives with even or odd. So that is exactly right. Why don't we just take it to 2 minus n plus 1? Would that work? It is injective. It's actually bijective. And it's the inverse of the one that Ray is suggesting in the chat, in case you're keeping track of that. The difference is that the function that Ray is suggesting goes the other way, right? It goes from the naturals to the integers and produces negative as an output. But here we want the negative to be in the input. Does that make sense? So if you ask all the people with a negative number, to take the odd numbered rooms, and all the people with a positive number to take up the even numbered rooms, there's infinitely many even and infinitely many odd rooms. So this has to work. There has to be enough space. And in fact, we can cram in way more people than this. We will expand this later. Right now, I want to talk about something else before we run out of time. So this would prove that the integers are countable. Now, if you look at the next example, someone in the chat suggested n cross n. N cross n is way more complicated than this, because n cross n is a grid, right? It's a plane. It's like a lattice plane. So now you have infinitely many rows, and each row has infinitely many columns, infinitely many elements. So how do you fit an entire grid into a line? So this is actually a little bit more challenging. We can definitely solve this now. Actually, why don't we go ahead and solve it right now? 5. Can we find an injective function? Can we find an injective? N cross n to n. That's weird, right? Because now we have all these pairs. So following the analogy of the infinite hotel, there's the number 0, 1, 2, 3, 4. And now, instead of having like an infinite line that goes to infinity on both directions, which is the integers, now we have, you can think of it this way. Now there is a bus. There is a bus. Bus. I'm really bad at drawing. There's a bus labeled 0, and that bus has someone labeled 0, someone labeled 1, someone labeled 2, 3, 4, and the bus is infinite, right? And not only that, but there's infinitely many buses, 2, 3, and so on. So how do you fit all of these people into the rooms? This seems way more difficult. What we just accomplished with the previous example was accommodating 2 buses, the positive ones and the negative ones. So 2 buses wasn't a problem, and you can easily expand that idea into n buses, right? Instead of thinking about even versus odd, you think about the modular classes mod n, right? Instead of splitting the hotel into 2 pieces, even or odd, you split it into whatever remainder you get from dividing by n. Let's expand this in a little bit more detail later, but right now I want to focus more on the intuitive part. So if anyone has an idea on how we can solve this, if you don't, I can tell you how. And the rationals are the exact same thing. Of course, the rationals are constructed this way. Let's see, some people in the chat are writing prime numbers. Okay, so prime numbers are indeed the way you can achieve this. With prime numbers, you can achieve actually a lot more, right? It's not just, with prime numbers, you can achieve, how do I say this? You could even achieve having infinitely many buses on a boat, and then infinitely many boats, each with infinitely many buses, each bus with infinitely many people. So you could recursively do this more and more complicated with prime numbers. Right now we just need two prime numbers. So F, the solution that I will leave you to ponder is we need to accommodate pairs of numbers, right? So n comma m, where do we send this to? This is the bus. Maybe I should put this in green. So the first number tells you what bus do you come from, and the second one tells you what row are you inside that bus, right? So if you come from bus number 17 and your row is 1,975,882, what is your room number? And make sure that that room number is not given to anyone else on any of these infinite buses, infinitely many infinite buses. What do we send this to? Let's think about that for a second. How do I make sure that there is no repetition? If you have no idea how to begin, then just, okay, so people are writing in the chat. Okay, so one suggestion is we add up the numbers and then we add them up again and add one to them and we multiply them. Okay, so I will just write down the suggestion that I was given in the chat and we're going to study it together. So we multiply them in this way. Okay, I'm getting multiple suggestions now. So the problem with the one I have written down right now is that there could be repetitions, right? So for example, the second bus, the fourth person, will get the same room as the fourth bus, the second person, because n and m are interchangeable in this. So this function that I just wrote down is not actually injective, right? It has infinitely many repetitions. So each room would actually have a lot of people in it, or there would be a bunch of rooms with infinitely many, I mean, maybe not infinitely many, with a lot of people in them. Okay, so now I have a lot of suggestions, and this is interesting because these are different. Okay, so we could take the nth prime number. That would work. Ray's suggestion with the nth prime number. I will go with the other suggestions just because they're a little easier to justify. So let me write down. Okay. Yeah, exactly. So if I take 2 to the n and 3 to the m, this function is injective. Why is this injective? Well, this is exactly, this is what the fundamental theorem of arithmetic says. It says that if you have powers of primes and they're equal, then the exponents are all equal because there's only one way to factor a number into primes. So I will let you finish this in case you haven't figured out why this function is injective. I suggest you write it down, and if you have questions next lecture or even today during Piazza, feel free to ask me, and I will expand upon this. This is one way of doing it. It is not the only one. Quick question. So this function is injective because of the fundamental theorem. Is this function a bijection? Maybe I can add this. Is this a bijection? Why do I want a bijection? I don't need one, right? I just want to show that this is countable, so I don't really need a bijection for that. But wouldn't it be nice if I have something like that, because that would be a stronger statement. Okay, Max is saying this is not surjective, and okay, sure. Any prime number larger than 3 doesn't work. Indeed. So this is not a bijection because it only hits numbers that are a power of 2 and a power of 3. It doesn't hit anything that's a power of any other prime number. So the number 7 is never hit, right? So the room number 7 will always be empty, even though the rest of the hotel has infinitely many people in it, right? So there's an infinite amount of rooms that are full, but there's also infinitely many rooms that are still empty. So this wasn't optimal. Even though we achieved our goal, this wasn't optimal. So my question to you is, can you find a bijection? Now, I haven't really argued with you why this should be the case, that such a bijection should exist, but it is actually not difficult, right? So we know, we just proved that this is true because we found an injection. We showed this, right? And it is easy. It is easy to see that n cannot possibly be bigger than n cross n because it is kind of like a subset, right? N is like a row of this n cross n grid. So it's just one of the rows of this plane. So a bijection must exist because of antisymmetry, right? But the question remains, can you find one? I mean, sure, I can prove that one exists, but can you give me one? How do I make sure that every hotel room has exactly one person? Now, before I continue, let me just mention one more thing about before we move on. So one last thing, that this is important for countable sets for a reason that I will have to explain on Thursday because we've run out of time. Let me just, one last thing about finite sets. That connects, one idea that connects to countable. Countability. So the theorem is, if you have two sets, finite, and let's make them disjoint just to keep things simple for now. Wouldn't you expect the union of them to have as many elements as the sum of the individual sets? This is important because this is how we're going to define this symbol later. How we're going to add up cardinals. How do we add cardinals? Well, just take the union and find the number of elements in that set. So this is something that we're interested in, right? If this makes sense. So how would you prove this formally, though? How would you prove this using the definition of finite sets? So A and B are finite, so there's some amount n and m that corresponds to them. Then we add it up. Then what do we do next? If this makes sense. You think about it, the idea is surprisingly simple. So we have A and we have B, and they don't touch, right? So let's say A has size n, and let's say B has size m. So here we are counting 1, 2, 3. We're starting to count from 0 just because I did it this way. It doesn't really matter too much. And then we have to keep going, right? So n plus 1, and all the way up to n plus m minus 1. And there's m elements in this part. And we have to somehow match these together. The ones in A are already matched, but the ones in B need to be shifted, right? They need to be shifted by, well, by n. Okay, so I'm getting some messages in the chat. Okay, so H has the same mapping. Indeed, that is correct, but we do need to shift it, right? We do need to make a small adjustment. So consider two functions, f from A to doesn't really matter what direction we pick, from n minus 1 and which g from b to 0 to m minus 1, right? This is how we are enumerating them. How do we know that these functions f and g exist? Well, because they are finite. That's the definition. So consider f, let's call this something else, maybe h from the union to n plus m, right? And we're going to send each element depending on where it is. If it was already in A, there's no need to do anything to it, right? We just assign the number that f assigned to it originally. But if it isn't in A, if it's in B, then we need to shift it, right? And we have to shift it by n. So we just do this. And I think this works. H is bijective, right? So I've mentioned this before, but the operations for finite sets are all well defined. Like they all make sense and they all behave the way that you would expect. Things get challenging when you apply these ideas to more complicated things like countable sets. What happens if you add two countable sets together? What you get is it still countable or is it bigger? You know? Do you know what I mean? So let me know if you have any questions about this. Is there anything that I need to clarify from the thing that I've mentioned? So for the next tutorial, some of which are, I believe, starting today, you will look at a lot more examples of proofs with finite sets, and you will basically cover all the basic operations in sets. So now I just told you how to do the sum. How do you add finite sets together? You can also multiply them, exponentiate them, stuff like that. And let me see, I have a question. Is n minus 1 an element of A? So not in this case, right? N minus 1 is simply the number. The set A has n elements, and they are labeled 0, 1, 2, 3, 4, all the way to n minus 1. So on this side, on the left side, I have the elements of the sets. And on the right side, I have the numbers that I'm matching them to. So if I want to use the definition of finite set, I need to match A union B to some number. And that number is, of course, this one. This one is the number, the natural number that I'm matching this to. Just adding them up. So n plus m, right? But in general, A and B could be sets that contain anything. They don't have to contain numbers. As you can see, we are starting to prove things that are starting to get quite counterintuitive, right? Like showing this with n cross n, and the one that we skipped, which is the rationals right here. This isn't obvious at all anymore. The fact that there's only countably many fractions is far from obvious, considering that in between any 2 points, there's infinitely many of them, right? And yet they are all the same amount. And on Thursday, we will prove that there are actually things that are no longer countable. We can actually find sets that are bigger, that have more elements, proving that infinities come in different sizes. Okay, let me stop the recording here, and I will stay inside the meeting in case you have any questions.